Thank you, Chris. That is a huge room. I need to make sure I take a picture so I can tell my wife I'm actually doing some work here and not drinking beers in San Diego. So my name is Sebastien. I'm from France. I hope you don't mind the French accent. Today I'm going to talk about Kubernetes operators and what I personally consider the hard parts of writing one. For the past year, I've been working on this project. We call it ECK, Elastic Cloud on Kubernetes. It's basically a Kubernetes operator to deploy the Elastic Stack products, manage your Elasticsearch cluster, like smooth migrations, rolling upgrade, and so on, Kibana, and APM server. You can check it out. It's on GitHub. The code is open. You can try it for free. But I'm not going to talk about ECK today. I'm just going to focus on building operators in general. So I will assume most of you already know what's an operator. But if you don't, I have a couple slides to remind you of what it is. So usually an operator comes with its own CRD, custom resource definition. That's a way of extending the Kubernetes API with your own set of APIs. So here, an example with Elasticsearch. The operator will come with its own schema that would allow you to define an Elasticsearch cluster. So here, we want to deploy Elasticsearch in version 7 with 3 master nodes and 2 data nodes. And users would just apply this YAML file to the API server, and that's the way we extend the Kubernetes API. Then the operator itself is basically just a pod running in the Kubernetes cluster. And what it does is watching resources in the API server. So here it would most probably watch all resources of kind Elasticsearch, but it would also probably be interested into watching pods, services, secrets, and everything we need to deploy an Elasticsearch cluster on Kubernetes. And the operator has this concept of a reconciliation loop. So whenever something happens in the API server, like a resource we're watching gets created, updated, deleted, it's going to trigger a reconciliation internally. And the reconciliation is just basically executing a flow of sequential steps. It doesn't have to be sequential, but most of the time it is. So that we eventually reconcile the expected resources we should have based on the CRD specification so that we have all these resources running on Kubernetes. So this reconciliation loop usually can really return early. Like say, for example, it's creating a set of pods. Probably we'll have to wait for those pods to be created before we can request the service that is in front of those pods. So instead of just waiting forever in a synchronous fashion, we'll just return early from the reconciliation. And whenever we get a new watch event, we would continue and start again the reconciliation, but probably we'll make some progress so that eventually we manage to reconcile everything we want. And this reconciliation runs over and over and over again. And most of the times, it just does nothing because everything's already there and everything's fine. But if something is not, it's going to reconcile things eventually. To help us writing operators, there's a bunch of tools out there in the Kubernetes ecosystem. And the one I used that I found really good is Kubebuilder, maintained by the API Machinery Special Interest Group. Kubebuilder basically helps you scaffold a Golang project to build your own operator. It helps you automatically convert your internal Go model to the CRD YAML representation and bootstrap everything related to the reconciliation we talked about. Behind the scenes, Kubebuilder is using the controller-runtime library, which sets up everything related to watches. It has this internal work queue concept so that any watch event triggers a reconciliation. I don't know if we have some maintainers of those projects in the room, but if we do, thank you, folks, because that's really helpful. OK, so that's it for the introduction to operators. Let's focus now on what in the team we consider the hard parts. There's really one thing I want to focus here, and that's this concept of the operator basically living in the past. So of course, the operator is kind of working in real time in the sense that whatever happens in the cluster, it's going to reconcile things over and over again. But you have to assume that every time that code gets executed, you're kind of one step behind the reality of things and the state of the world. Let's take an example here. Say, in the middle of my reconciliation, I need to list all the pods I have in the cluster related to my particular application. So I would list the pods, and I would see maybe I have 2 pods, pod A and pod B. And then compared to what I expect, which would be having 3 pods, I realize one is missing, so I need to create it. So I would create pod C here, and then if later on in that same reconciliation, or maybe the next reconciliation, I list pods again, I would probably expect to have 3 pods now. But what I will most probably see here is that I have only 2 pods, because pod C is not there yet. It was still created, otherwise I would have got an error, but I don't see it. I don't see pod C here. And that's not a bug, that's a feature. That's by design. The reason is the client we use to reach the API server uses a cache reader, which means we are not sending a request to the API server every time we want to list things or get a particular resource. Because that would be pretty expensive. That would be a big performance hit. So what we do instead is that we have this local cache to the controller, and the cache gets populated from roach events. So whenever we need to list things, we just look at what we have in the cache. This can lead to some funny situation. In the history of our project, we had several bugs that are related directly to this usage of the cache. Things like creating too many pods, like you expect 3 pods to exist, but because every single reconciliation creates one based on an out-of-date cache, you actually end up with 25 pods after 3 seconds. Or if you need to manage stateful workloads like Elasticsearch or any complex distributed system, pretty often you have this notion of quorum, where you have a set of master nodes, and you need to make sure somehow that you maintain some kind of consistency here. For example, in the case of Elasticsearch, if it's running 5 master nodes, you need to make sure that 3 master nodes form the quorum. So if your assumption on the number of nodes relies on the number of pods you have in the cache, you may have a problem here because your cache does not really represent reality. So what can we do about it? Well, we're lucky because in most situations it's just fine. We don't have to worry about it. The reason is Kubernetes has this concept of optimistic concurrency implemented there by default. When you do a creation, the resource you create has a name and probably a namespace. Say, I'm creating 1 pod at 1 reconciliation, and at the next reconciliation, I'm trying to create the exact same pod because I don't see it in the cache. The API server is probably surely actually, going to reject that creation because another resource with the same name already exists. So in the reconciliation, I would get a conflict error, and that's just fine. If I get that, I just return early from the reconciliation. And another reconciliation is going to be queued again whenever there's a change in the resources I watch. So whenever that new pod I created appears in the cache, a new reconciliation is going to be triggered. And this time it will probably not fail with the conflicts because I'll notice the pod is there, so I'll not try to create it again. We had the same kind of stuff with updates. Every resource has a resource version. So whenever you do an update of a resource, what you can do is, with your update call, you ship this resource version that you have from the cache. And if the resource in the API server does not match that version, so probably it has been updated concurrently with what you're trying to do, then the update operation is going to be rejected, which is fine because I probably don't want to update a resource based on incorrect assumptions on what I observe. Deletions basically work the same way. So here I'm using the controller-runtime client to talk to the API server. And whenever I do a deletion, I can just pass in the UID of the resource I want to delete and also the version of that resource. So I don't, for example, by accident delete a resource I would probably not have deleted if I had the proper version of that resource. This is also kind of useful if you're dealing with stateful sets, especially if you're using the onDelete strategy. We'll talk about that later. What could happen is that you delete a pod, you expect the stateful set controller to recreate that pod. But at the next reconciliation, maybe you would do that deletion again. But if the stateful set controller already recreated the pod, it gets a newer ID. So you're actually deleting again the pod that was just restarted, which is not what you want. So shipping the UID here in this call helps with that. So this is all fine, but in some situations, that's not enough. I said earlier that whenever you manage stateful workloads, you have this additional complexity of maintaining some kind of consistency between two systems. On one hand, we have the Kubernetes resources, and on the other hand, we have this external, maybe distributed complex system to operate. And we need to make sure that there's some kind of consistency here. And the API server optimistic locking does not always help with that. So then, if you reach that situation, like you write some code, you know what you want to do, but you realize even though optimistic concurrency helps, that's not enough. There's a risk you can do something wrong here. Then you can use something else. And we actually found that in the deployment controller, and more specifically in the replica set controller, because when you create a deployment in Kubernetes, basically there's the same problem. When the deployment decides it needs to scale and create new pod, you don't want it to suddenly create 15 pods instead of one because the replica set controller was making decisions based on an out-of-date cache. So the way it works, the expectations thing, is that whenever we do a creation, like here, whenever we create a pod, at the same time, we register in memory the fact that we did this creation. So we expect that creation to happen, and we expect that at some point, this pod will appear in our cache. Then at the next reconciliation, when this gets executed again, before we do any other creation, we look at those expectations we registered. Is that pod we created before actually in the cache yet or not? If it is, that's fine, we can move on. But if it's not, we should just return early, because we'll retry later eventually. So in the replica set controller, this is all bound to watching creation and deletion events. In ECK, we try to make it a bit more generic and simpler in a sense. So every time we need to check expectations, we just look at what we have in the cache. But that's a pretty useful concept if you need to use it. If you don't, not use it. I have a few set of best practices so that whatever you write in the reconciliation actually helps you, saves you from doing anything wrong. And the first thing is to use deterministic naming. We saw earlier this optimistic concurrency on creation, which works fine as long as the resource you create has this table name. So you create it the first time, you're sure you're not going to create it a second time because the second creation will be rejected. But if the resources you create have a random name, then this doesn't work, right? So you need some kind of stable deterministic naming. For example, if you use stateful sets, you'll notice that every pod, underlying pod that gets created has the name of the stateful set plus an ordinal. So that's very deterministic. The stateful set controller knows exactly what's the name of the pod it's going to create. Then at any point of the reconciliation, you have to assume that probably your cache is stale. You have to think about it. Like whenever you do something, try to think, what if the resources in the cache are not up to date? Is everything going to be okay? Most probably yes, but sometimes it isn't. And finally, the entire reconciliation should be idempotent, which means it's going to run over and over and over again. You want the output of this reconciliation to be the exact same state of resources in Kubernetes. it's really fine to retrigger the same reconciliation. And at the same time, if anything goes wrong, like if a pod disappears, if a service disappears, if a secret disappears, you're pretty sure that the next reconciliation is going to fix things up eventually. An example about that, say, I want to create a stateful set. So like a simple version of how I would do that is first check, does that stateful set exist already? And if it does not, then I just create it. But then, as you probably know, when we create a stateful set, we most of the times also create a headless service for that stateful set. But here we have a problem in this piece of code. What if the operator crashes in between those two creations? We create the stateful set, there's a crash, the operator gets restarted, and we don't go through that code path again, so we're actually never going to create the headless service. Or maybe the call to the headless service creation returns an error, and whenever we're going to retry that, we're actually not going to retry that, because the stateful set is already there, we created it, so we don't enter the if condition again. So one way to fix that, of course, is to reverse the ordering. Since our condition is based on the presence of the stateful set, if we create the stateful set last, then it's okay, because say we create the headless service, then the operator crashes, then when it's going to start again, the stateful set is still not there, so we'll do that again. But still, probably, this is how you really want to do it. You want to decouple the creation of every single resource. Because the problem with that second version is that if someone accidentally deletes the headless service, it's never going to be created again, because we'll never enter that code path. And here, if we try to keep things flat, then we're pretty sure whatever happens, if the stateful set is removed, if the headless service is removed, then the next reconciliation is going to fix things again. So usually, it's very interesting to keep things flat and sequential, even though it sounds a bit stupid, which doesn't mean, by the way, that the entire reconciliation needs to be like a single big function of 2,000 lines of code, right? It's just the way things are executed that matters. So I talked about reconciling resources. Handling creations and deletions are actually fairly easy, but handling updates are sometimes very hard. Say, whatever you have in your CRD internally maps to the creation of a stateful set. And maybe that CRD resource was updated so that now you know you should update the underlying stateful set from 3 replicas to 5 replicas. There's an update operation here you need to do. And usually what happens is that internally in the code, you build this expected resource that you'd like to have in Kubernetes. And you compare that with the actual resource you have that you fetch from the cache. And then, based on this comparison, you decide whether you need to update the resource or not. So how do you do that comparison? Well, a naive way to do that would just be to use reflect.deepEqual. So if the 2 resources match exactly, that's fine. You don't need to update. Otherwise, you need to update. But that doesn't work quite well because, here. Say on the left, I'm creating a pod. It's a minimalistic pod. I create it this way. Then if I retrieve it, that's what I get back. That's not exactly the pod I created, right? There's a whole bunch of metadata that was added by Kubernetes. Also, that pod creation went through a whole lot of mutating webhooks. And for example, here, things like image pool policy was added. Maybe I have a limit range in the cluster, so now suddenly I have resources requests in the pod spec. And also maybe I have a bunch of environment variables that were added. Here, that's what happens, for example, if you do that on Azure Kubernetes. So obviously, you understand we cannot just reflect.deepEqual these 2 resources. It doesn't work. What can you do then? Then you can try to go one step further. You would build custom comparison function for every single field in the spec. And then you end up with this super big list of comparison functions that you execute that are very hard to maintain because there's always something you didn't plan. Like you didn't plan this new label to be added. You didn't plan this new environment variable, so you need to patch the code again, and it's never ending. So how can we better handle that? We looked into all the controllers that are there already in Kubernetes and try to find if they have this problem as well. Turns out they do, and the way the stateful set controller handles it is pretty interesting. Whenever you update a stateful set, there's this concept of revision. So the update of the stateful set spec leads to a new revision of the stateful set. And the way this revision is built is that it's actually made from a hash of the spec of the specification of the stateful set at the time it was updated. And to know if a new revision is necessary, well, we just have to compute that hash again and see if there's already a revision that exists with the same hash. And here we can actually use the same concept. Whenever we create a resource, we can build a hash of that resource. So building a hash can be done in multiple ways. The way it's done and the way we do in ECK is that we just build like a string representation of the object using a library called goSpoo, and then we hash that string, which gives us a small hash, like a few characters, that we actually store in an annotation in the resource. So that later on, say in a subsequent reconciliation, when we want to know whether we need to update that resource, we just build a hash of the expected resource we want, and we compare that with the hash of the actual resource. And if they match, then we don't have to do the update. If they don't, we need to update. So the real smart thing here is that the actual hash is built at creation time. So it does not care at all about any field that was patched by Kubernetes, like any metadata that was added, any new environment variables or whatever, any mutating webhook patch. So really, we compare hashes of the resource at the time it was built, not at the time afterwards that it was patched. And it's pretty interesting to use whenever you need to reconcile some complex resources. Usually when we build CRDs, we try to build an abstraction of reality, so users don't have to care a lot about what happens on the underlying Kubernetes cluster. If you want to deploy a 3-node Elasticsearch cluster, you don't care about the underlying pods. So we can build this really minimalistic, simplistic version of the CRD with only the fields you care about. But in reality, what happens is that most users want to do more. They ask us, hey, can you add this feature so that whatever pod created by the operator actually has this particular label, or maybe give me the power to change the affinity rule of the pod so I can do zone awareness in the deployment you control. And turns out the best way to do that is actually to empower the user completely to do whatever they want in the CRD. And that's what happens when you create a stateful set or deployment. You have this pod template that you can specify entirely. So here, for example, in the operator, what we do is that we have this optional pod template section. Users can do whatever they want here. And in the reconciliation, when we build the expected pod we want, we take that template from the user and we build on top of it. We add our own fields in there. And if they're already specified by the user, we don't touch it. That's kind of the user responsibility. So they can shoot themselves in the foot if they want to. Usually they don't, because you kind of know whether whatever you're specifying here may or not break things. Finally, I'd like to end this presentation with a few things about stateful sets that I learned and persistent volumes that maybe you don't know about, and they are really interesting whenever you want to build operators that are managing stateful workloads, which, by the way, are a pretty good reason to use an operator. Like, stateful sets by themselves are nice, but if the workload you manage is a bit more complex than what the stateful sets allows you to do, operators are a pretty good way to solve that. One first thing is that you cannot resize volumes in stateful sets. It's not supported by the stateful set controller. Actually, if you create a stateful set and you give each replica 10 gigs of storage, you try to update it, you cannot, because that section in the stateful set spec, like the volume claim template, is immutable. You cannot change that. Luckily, there's a cap in progress to fix that. I'm not sure it's going to land in the next version of Kubernetes, but there's an issue for it at least, so it's good. So what can you do in the meantime? There are some workarounds. You can do things like delete the stateful set, but keep the pods around. Then behind the scenes, you resize the volume, then you recreate the stateful set that takes control over the pods again, but that's pretty hacky. The way we do it right now in the ECK operator is that whenever we need to change the storage requirement of a given stateful set, we actually create a new stateful set with a new storage requirement. We just migrate data over the old pods from the new ones. And because it's Elasticsearch, it's kind of easy to do. We can just migrate shards from some Elasticsearch nodes to some other. So we bring up that new stateful set with the new storage, we migrate the data over there, and once it's done, we remove the old stateful set. Another important thing about volumes is the way storage classes are specified. So you probably know that whenever you use persistent volume, what you usually do is first create a persistent volume claim specifying which storage class you want, and then the controller is going to bind that claim to an actual persistent volume. And that's actually what the stateful set controller does, for example. It just creates a persistent volume claim and then creates a pod that is mapped to this claim. Here in the storage class, there's this important field called the volume binding mode. And if you don't set it to wait for first consumer here, for example, what's going to happen is that you create a stateful set. The stateful set controller, whenever it needs to create a pod, is going to create the persistent volume claim first. That persistent volume claim is going to be bound to a persistent volume. But maybe that persistent volume has some affinity constraints so that the volume is only available in a given region. Or maybe it's a local volume, so it's only available on a particular host. And then the stateful set controller creates the pod, mapping that persistent volume claim. And what could happen is that the pod itself is scheduled with its own constraints, so maybe on a particular region or particular host. And it's possible that the place where the pod is scheduled cannot actually access the volume, and that's a big problem. And to solve that, there's this wait for first consumer option, so that the pod is scheduled first, and then the volume is created based on the constraints of the pod. And I'm actually surprised that most persistent volume available out there in many cloud providers don't have this enabled by default, don't have this option set. And in many cases, you can just do it yourself. You can patch the existing persistent volume storage class available and use this option. Or maybe just clone it to a different storage class with a different name, which has this option because it's really important, especially when dealing with local volumes. Another funny scenario that we encounter is when dealing with local persistent volume. So maybe you're just using the disk attached to a particular Kubernetes host. For that, you're using a local persistent volume. Now, what happens when you need to upgrade a stateful set because the spec changed? Normally, what would happen is that processing pod by pod, the stateful set controller would delete a pod, then recreate it in the new version, and then it's going to reattach automatically the same persistent volume, all thanks to deterministic naming, by the way, because turns out if we take the name of the pod and we use the same name for the volume, then it's pretty easy to match them. But here, between operation 1 and 2, what could happen in your Kubernetes cluster is that another pod gets scheduled concurrently. And it's actually taking the resources that were necessary to recreate that pod that was deleted. So you expect a stateful set upgrade to go through, like pods are deleted and recreated one by one. But if in the meantime another pod gets allocated to a particular host where your pod needs to be recreated, then you have a problem because that pod will then stay pending forever. And this scheduling concurrency here can be a bit of a problem. Then, whenever you deal with stateful sets in an operator, you really have to pay attention to the update strategy you pick. So by default, stateful set works in such a way that each pod gets rotated one by one when you do an upgrade. So it's based on the readiness of the pods. If all 3 replicas are ready, I can upgrade the first one. Then when it's ready again, I can upgrade the second one, and so on and so forth. And if that's fine with you, chances are you may actually not need an operator at all because you can just create stateful sets and it just works, right? But if you really need an operator for something else because you need some kind of control over the way rolling upgrades are done, for example, then probably this default strategy of upgrading will not be good for you. And luckily, we have other choices here. We can rely on the rolling upgrade partition. This is an index in the stateful set spec that says every replica having an ordinal higher than that particular index can be safely rotated and upgraded by the stateful set controller. For example, if I have 3 replicas, and in my operator I set this rolling update partition to 2, it means the stateful set controller can safely upgrade the replica number 3 because probably on my side of things in the operator, I did whatever's necessary so that the upgrade of that pod is fine. Another way to deal with that is to use the onDelete strategy. And the way it works here is that in the operator yourself, you have the responsibility to delete the pods you want to upgrade because you know they can be safely deleted. Maybe, I don't know, you migrated data away from them or you kind of prepared your workload for that restart. And then as soon as they are deleted, the stateful set controller, which is in a way also an operator, so a controller, will reconcile the stateful set resources again, and it's going to recreate the pods itself. So if you need to deal with stateful sets, ask yourself the question, what's the best strategy I can use here? And most probably, if there are some calls you need to do for an upgrade to be performed, you'll not pick the default one. But it's flexible, so it's very good. Finally, what I wanted to say about stateful set is you don't have to use stateful sets to manage stateful workloads. What are stateful sets really? It's just a way of creating a pod and binding that pod to a persistent volume. Thanks to deterministic naming, you know that if that pod gets killed and you need to recreate it, and the volume actually already exists with the same name, you can just match and bind that volume mounted to that pod. So that's actually possible. You don't need the stateful set controller to do that. You can manage things yourself. We tried. What happened in reality is that we implemented a slightly different version of the stateful set controller within our operator, which is probably not something you should do. There are dragons everywhere, and stateful sets are there for that particular reason. That's all I wanted to say today. Thank you for listening to me.